Good morning, everyone. Thanks for coming. Be talking about QuteFuzz, which is a quantum compiler fuzzer, and it uses randomly generated circuits with control flow and subcircuits. And this is a joint work by me, Ilan, and John Wickerson, but Ilan, he couldn't join us today due to technical issues. So let me begin. So before I explain how QuteFuzz works, maybe I'll give you a bit of an introduction. So we are currently in the NISQ era, and oh well, not so much now given the previous talks, but at the time of writing, we have limited logical qubits to work with, and their states are quite error prone. And therefore, we need these quantum compilers to produce optimized circuits and shrink down the size, optimize layouts. And these quantum compilers are used in these like Qiskit, Cirq, and PyTicket, which are like major quantum software stacks. And we have a nice diagram here showing just how a quantum compiler works. On the left, you can see it's like a pretty complicated circuit. We put it through some passes, and out comes a nice circuit that's a bit simpler. Right. So why do we want to test these quantum compilers? Well, these are the tools that we will be relying on to make the circuits that we will be coding out more optimized. Therefore, if these quantum compilers like alter the semantics of a circuit and gives you a different results, that would be really bad, or it might just crash, which we have found some bugs like this. And finding these bugs will help us prevent similar bugs happening in the future as well. So we're not the first to do this. These are some of the notable related work. So QDIF is one of the earlier ones done by Jiyuan Wang et al. And they started out with 6 handwritten programs, which then they mutate to generate 15,000 test cases. And they found a few bugs as well. And MorphQ, which is pretty much the same thing, but they added subcircuits to it, which is done by Matteo Paltenghi and Michael Perdell. So what does QuteFuzz do on top of these? What are our main contributions? Well, we generate completely random circuits, so we're not mutating from any C programs, which allows us to generate a lot more circuits at one go. And we really focus on subroutines and control flows in QuteFuzz. So just a quick recap. Subroutines are basically like groups of gates that you can kind of like just add to a higher level circuit. So you don't need to rewrite some code. That's as far as I understand. And control flow is, as explained earlier, it's like if you measure a qubit and it gives you some result, it will append some gate, or else it's something else. Yep. So now that we know what the quantum compiler is and why we need to test it, so now I'll tell you more about what QuteFuzz is and what it does. So quantum compiler fuzzing, fuzzing in general, you need random inputs. So over here, we can see that we have a generation loop here. We follow these 4 steps, basically. First, we generate the imports, then we generate the subcircuits, which will be used in the top-level circuits, which we call main circ in this case. And then we call language-specific tests for PyTicket, Cirq, and stuff because they have different simulators. And then, we do this for all 3 quantum software stacks in here. We do differential testing where we take the circuit, we get 2 copies of it. We put one without compiler through the simulator and one with. And if the result's different, then there's a problem. So let me give you perhaps a live demo. I'm not sure if you can see this. So this is QuteFuzz. I'm just going to generate some random circuits in Qiskit. Oh, all right. As you can see here, these are 10 unique different circuits. Let me just extend this. It has the general structure here, the imports, define the subcircuits. Oh, there's quite a few here. Then the main circuit, in which we have some control flow. The measures are there to measure the qubit state, and then if If it is true, then we append this, or else we append that. I can do this for others as well. So these are circuits. Oh. It's pretty fast, and we can do pi ticket as well. Yep. So, right, moving back, can skip these. This is just a nice circuit that, actually this circuit kind of found a bug, so, and it kind of have everything in it. As you can see here, the control flows and stuff like that. And at the end over here, we run Parson Simulator is basically a function we call to test these circuits, which I'll explain later on. But here's how, and I know you can't really see this, but this is how the circuit looks like. This is our randomly generated circuit. So how do we do differential testing? Mainly we use two methods. One is a state vector comparison, since each quantum circuit would have an output state vector, and we just compare whether it's equivalent or not. And if it's not, then we know that something has semantically changed. And KS test is for other cases where we don't have state vector output. So in the case of Qiskit, I believe, wait, actually it's in the next slide. In the case of Qiskit, where we apply control flows, we do mid-circuit measurements, which where the simulators cannot give us a state vector output. In which case, we'll use short-based simulation. And with that, we can use KS test to, in a way, compare these two output distributions and whether they are the same or not. Right, so another demo. This will be on this circuit that I've prepared before. So what happens is, I'll run this. Oh, it's a bit slow, sorry. As you can see here, this is short-based, and we got like a really, really low number here. And maybe I could plot this out to show you. Right. Yeah, so this is the original. And after compiling, we got this. So it's very different. Something's wrong. We logged that in. And we've made a Python script to like automate all this. So let me do that now. 3, 1. So I'm going to generate Qiskit circuits. I'm going to do 10 of them. See, it generated some circuits, and it's just running through them. You can see here in results, yep. So for circuit 1, we're using this pass called optimised at 1 QGates, and we're using state vectors simulation. And as you can see here, if it's the same, it's good. If it's not, like we've seen earlier, then something's wrong. Oh, it just finished. Right, so moving back. Okay, so through this method, we found 17 bugs in total across Qiskit, PyTicket, and Circ. Of those, 12 were compiler bugs. 5 of them were simulator bugs that were found just because simulators were part of the stack. And these were found from running over 500,000 test circuits, which was only possible because we were doing random circuit generation. Of these, 3 bugs are fixed. One of them currently unacknowledged, while all others have been acknowledged. Nice graph here, show that. And so of these are some interesting bugs that we found. The first one actually is where we've seen earlier. Let me just very quickly show you the issues page. Right, so this one, it's a very nice diagram. We've managed to narrow down the test case. So after random generation, we managed to narrow down the problematic parts to just this, which is very small. And what happened is basically this turned into this, which was not right, and it was fixed. Here's another one. So it's, again, in Qiskit, and specifically to do with optimization levels 2 and 3. And we found out that, again, there was a miscompilation. And it turns out that there was this thing called consolidate 2Q blocks, which had a unitary matrix that had 2 values that was swapped, I think. and that caused issues. And over here, we have for circ. So in this case, an empty subroutine caused an error on the simulator. That was fixed as well. And lastly, for ticket, this is, let me just go back to the slides. Yeah, the compiler will crash when two subcircuits are adjacent to one another. So what do we learn from finding these bugs? Well, for one, there is perhaps a need for better test suits for these quantum compilers. So for example, the second bug here, where there's optimization levels 2 and 3, and the unitary matrix was like not correct. Well, it was introduced later on in one of the patches, and it just didn't occur to them that that would happen, and they didn't include that in their test case, and that was a bug. And another thing to note is that despite the size of the circuits QuteFuzz generates, which are big and sometimes maybe not really realistic, like you wouldn't like generate something like write something like that manually, but the bugs were reproducible using really small circuits that were reduced from these test cases, which means that QuteFuzz can detect these genuine errors that a regular programmer could have written. Right, so here are some of the future work that we hope to do on QuteFuzz. First and foremost is to allow the user to customize some circuit parameters. So for example, circuit depth, the number of qubits, or maybe even control flow depth. So like how much nesting there are. These are currently hard-coded. We just kind of like winged it and gave some numbers, but we hope to be able to like customize that so the user would generate some pretty nice circuits. We also like to do cross-QSS testing, whereby we could generate a circuit in Qiskit, put that through their simulator, and maybe generate the same circuit in circ and put that through the simulator and do differential testing there, which would be quite interesting. And lastly, we would like to have done some kind of, we'll improve on our circuit generation techniques through some kind of AST, whereby we can generate the structure of the circuit, maybe like here, where you can generate the structure of the circuit inside of the tree, and then apply that to specific languages so that we can test different languages without completely revamping all the code and stuff. And that marks the end. I'll be taking questions. Oh, hello, Ilan.
Hello, can you hear me?
Yes, okay, perfect.
Oh.
So let's take just a couple minutes before the break for some questions. Both of you.
Very one. Yep. Hello.
Hi, thank you for the very interesting talk. I was kind of curious how you define circuits to be equivalent, because when I think of like compilation, one of the first things that come to mind is like maybe decompiling a Z gate to Clifford plus T. And usually the standard thing you might do is that's usually up to some error. So the output of the compiler wouldn't actually be semantically equivalent. It would be semantically equivalent up to some error when you're doing like compilation to certain gate sets. Can this tool handle those kinds of cases, or is it just looking at like exact equivalence right now?
Exact equivalence. As for state vectors, I think that's we're just comparing the output state vector. But for like short-based, I'm not too well versed in the quantum world, but as far as I know, so I think over here, KS test, which is the test that we just saw with two different graphs. My understanding is that, well, your compiler shouldn't modify the output distribution of your circuit. And if there was any change, like significant difference, like what we just saw, then, well, it's an error a bug that we want to find and fix, yeah.
Yeah, I guess like the case that I'm thinking, there wouldn't be any significant change. So yeah, I guess that kind of captures that. Thanks.
Thank you.
So I guess this kind of springboards off the first question. So have you tried kind of verifying results of compilation that target different technologies?
Different, what do you mean by different
Or, so
technologies?
different gate sets. So maybe like one for like a superconducting circuit or one for like a chopped ion machine.
I don't think so. This is kind of like one level up, I think. So we do not have that kind of, like, we don't know whether this circuit is for different technologies or not. We just, yeah.
It's
Yes.
very interesting. I think it could be a good research direction. Or maybe if you wanted to do like test-driven development, you could have this be a test in a compiler.